Hello students, in the last video we have discussed about Chomsky hierarchy of languages and the relation between the classes of the languages. So as I told you in the unit 2 we have discussed much more about the context-free grammar, the most widely used grammar. And compared to CFG, regular grammars are not popular, but compared to unrestricted and CSG, the regular grammars are popular, and of course they are the most restricted grammars. And we have already discussed about the rules of regular grammar. Let me just go with quick recall of the definition what we have discussed in the last video. Let me go with this. See, regular grammars where we are going to use it. See, regular expressions, DFA, topological space, function representation, set theory, logical theory, semi-groups. So these are the applications of regular grammars. So we have already discussed about some of these here, regular expressions, DFA and sets, right? Not the logic theory. So what first of all, what is mean by regular grammar? So every production must be in the form of, we have already discussed, right? A terminal followed by a non-terminal, or a terminal alone, or a non-terminal followed by a terminal. In addition to that, we can take the epsilon, where they have clearly mentioned that x is t star, right? Of course, only one symbol is allowed, guys, right? Not more than that. Then these regular grammars are categorized into two types, left linear grammars and right linear grammars. What does it mean by left linear grammar? In every production, the non-terminal must be in the leftmost position. Means if you have two symbols, first should be the non-terminal. The non-terminal must be the left one. And in right linear grammar must be the rightmost symbol. So guys, the power, the languages, if it is left linear, can be converted to right linear. If it is right linear, we can convert it to left linear. There's no problem. Okay. And while you are converting, even we can convert the grammar to finite automata also. We'll discuss about that. So now, why we need to go with the left linear or right linear? Generally, if you are saying that it is a regular grammar, okay, then you can write a non-terminal followed by a terminal followed by a non-terminal, or alone terminal or epsilon. For example, you take this grammar, S tends to AS or SA or A or epsilon. So this is a regular grammar, right? But this is not a left linear or right linear, because here we are having both left linear productions and right linear productions. Now if you say that left linear, only left linear, you can take like this, S tends to AS, right, or A or epsilon. This is right linear grammar, sorry, right linear grammar. And if you want to say that left linear, you can write S tends to SA or A or epsilon. So this is a right linear grammar and this is a left linear grammar. And the language accepted by those three, these three are same. Just it will give you any number of A's. That's it, not more than that. Just write, it will give you any number. So for the same language, we can write a general regular grammar, which may have both left linear productions, right linear production, or we can write only left linear grammar, or we can write only right linear grammar. Then you may get it out. Then why we should discuss about the left linear or right linear? See, while you are writing your own grammars, regular grammars, you don't need to follow the linear rules. But if you want to convert this regular grammar to finite automata, then first and foremost thing, you must specify the grammar either in left linear or in right linear. Otherwise, we cannot convert into the finite automata, right? So then how you can do that conversion, we'll discuss, right? How to convert a finite automata to regular grammar if you're having like this. See guys, the finite automata is generally denoted with the 5 tuples like Q, sigma, transition, Q naught and F, where Q is a set of states. And the grammar, if you are converting into grammar, it is represented with non-terminals, terminals, productions and the starting symbol. So same way here in the grammar, if it is a non-terminal and you are converting the machine to grammar, then the non-terminals are nothing but the states. Okay, here what are the non-terminals in this case? The states here, those are nothing but A comma B. And the terminals are nothing but input alphabet. What it is? A comma B. And productions, I'll tell you how to write it. And the starting symbol, is nothing but the starting state, which is nothing but A. Then how to write the productions? It's very easy, guys. Just listen here. Then you may get it out. What is the effect of acceptance states? So we don't have any accepting non-terminal in the grammar, but what is its effect? How we are going to represent it, that I'll tell you. Don't worry about that. But let me go with this. So first let me write the productions here. Productions are nothing but the transitions, what it would be. See, on A, if I read B, where we are going B, then you have to write it. So on A, if I read B, I'm going to B. So if B is a final state, then you have to take the terminal alone. Right? You can take the terminal alone. Right? As B is a final state. Same way, on B, if I read A, where we are going B, as B is a final state, you can take it alone. Right? On B, if I read small b, where we are going capital B, then as B is a final state, you have to take the B alone. That's it. So this is how it is going to be given. So why, right? Of course, here it is epsilon is missing. Then why they have given here, sorry, not epsilon, B is missing. Okay, don't worry about it. Anyway, we have given the answer, right? That's the reason I'm explaining here also. Now, why they have not given here? So because they have taken the epsilon. So if you replace the B with epsilon, you are going to get the B. And if you replace this B with the epsilon, you are going to get the A. And if you replace this B with the epsilon, you know how to eliminate the epsilon rules, right? Then you are going to get the B. Same. So this is simplification, not simplification, sorry. They are just enhancing the grammar rules, reducing the grammar productions by introducing the epsilon. So that's your wish, guys. What do you want to take? But simple, very simple here. Let me explain once again quickly. So after identifying it, how to write the productions. A, outgoing edges. B, we are going to B. As B is a final state, then you take the B alone. Otherwise, you stop with that only. And B tends to, if it is B, we are going to A, we are going to B. As B is a final state, you take A alone. And if I read B, again I'm going back to the B, then as B is a final state, you take it. For example, if I'm having A here, assume that. So on A, if I read A, where we are going A, but don't take the A alone here, because A is not a final state. Capital A is not a final state, then don't take it. For example, if you are having like this A, then you can write it. So on B, if I read, we are going to capital A. As A is not a final set, don't take it alone. That's what I'm trying to explain. That's it. Then even we can convert the regular grammars to finite automata also. See, the grammar is represented as 4 tuples. What is it? N, T, P, and S. And machine is represented with the 5 tuples Q, sigma, transition, Q naught, and F. So here Q is nothing but the non-terminals what we are having here B comma A, right? And sigma is nothing but the terminals what it is small a comma small b. And transitions are nothing but the productions. We'll discuss how we have to write it. Then Q naught is nothing but the starting symbol what it is B in the starting symbol here. Okay. Then what is the final state? How to identify the final state, guys? See, if you are saying that a state is final state, and whenever it is occurred with some production, that should be alone occurred also. If you are saying that B is a final state, then this A would have been here, but it is not, right. Then B is not a final state. It is not a final state. So then A, see AB, if A is a final state, B would have been occurred alone. AA, if A is a final state, A would have been occurred alone. Of course, then I can conclude that A is the final state. This is how we are going to identify the final state. There is no other way to do it. That's the only way to do it. Okay. Then after identification, then take the states. What is it? B and A. You can do like this. B and A. So A is the final state, B is the starting state as we have discussed here. Then see, guys, B. If I read A where we are going B itself, then take the self loop. And if I read B where we are going B itself. And if I read B where we are going A, then you no need to worry about this. As it is a final state, we have taken it. No need to worry about the single terminal productions. And A, if it is A, we are going to A. That's it. So this is how we are going to convert a regular grammar to finite automata. Right? So then even we can convert a left linear grammar to right linear grammar also. So for example, we have a left linear grammar and that we have converted into the automata. Simply interchange the final states and non-final states. Sorry, interchange the final states and starting state and just reverse the edges. Logic is very simple. Here it is starting state and final state, right? Then make this starting state as a final state, make the final state as a starting state, and reverse the transitions. So B we are having reverse it, A comma B, and reverse is B. That's it. So we are just converting the left linear grammar to right linear grammar and right linear grammar to left linear. Just do that, and after that we can convert into the finite automata. And the last one is unrestricted grammar. It is also type 0 grammar. As I told you guys, in exam, most of the cases you will get the question from this regular grammars, left linear, right linear, context free grammar, parse free. The remaining two grammars, context sensitive grammar and unrestricted, you will be asked what are the rules of it and what is the relationship between other, what is its number, what is its machine, what is its language, right? In the last video we have discussed the relationship between all those, right? That so an unrestricted grammar is also called as type 0 grammar in the Chomsky hierarchy. So how to remember these numbers, right? Unrestricted means what? No restrictions. If you count it, no restrictions means 0, type 0. That's how you have to remember it. Okay. And of course, it is the most powerful type of formal grammar compared to any other, but it is restriction free. The regular grammar is not most powerful. The power is only regular languages, but it is more restricted, right? So it is a formalism used in formal language theory and theoretical computer science to describe the language in any way that is more general than the context sensitive. So it is giving more flexibility so that we can represent many languages. So unrestricted grammar has very few restrictions on the rules governing the productions of strings in the language. Not few actually, we don't have any restrictions generally. The only restriction we have is the left hand side we should have at least one non-terminal. So that's the only restriction we are following here, right? So in the last video of ALC we'll discuss about context sensitive languages and its machine, that is linear bounded automata.